quick presentation of the functioning of the DAC acquisition board from Alex, Paul and Dean. I'm just going to start off quickly with showing you the impedance file, which is basically this piece of code here. The reason for that is I'm just memorizing in MATLAB all my important values for resistor, capacitor, time constant, reactance, impedance, and the example of the voltage out with the frequency of 1000 Hertz. So I'm just going to run that first, and there we go. We have a bunch of different values. First, time constant being just a product of the resistor by capacitor, which is 0.1. Reactance at 1000 Hertz being minus value, because the reactance with capacitors always acts along the negative J-axis. The impedance at 1000 Hertz is given as the complex number. So since we have that in the memory of the program, we can jump straight into the square wave, which is this piece of code right here. From last year we should know that to fully charge a capacitor we need 5 time constant. 5 by time constant gives us 0.5 of a second, which is pretty fast. I'm just going to run that, and here we go. The user is asked to enter the peak-to-peak voltage, which is any value. Let's just say 10. Enter frequency of 1 Hertz, and here we are given the voltage out in Cartesian form right here, and the magnitude of it. And the reason for magnitude being relatively big is because frequency was relatively small, and that's one point to remember. When magnitude decreases, frequency increases, and vice versa. So there you go. We can see that the capacitor did not reach a fully discharged state yet, and here it's at 59. Should be at 0, or around 0 actually, I should say. And we can see after one cycle, which is one square wave, we reach 99.7, as far as I remember, percent of the voltage supply, or the voltage being sent in. So this proves that our RC circuit works correctly with square wave. And I'm just going to quickly jump into the sawtooth wave. This is just another example of a signal being used. This is this piece of code here. I'm evaluating selection. Again, peak to peak voltage, let it be 10. Frequency of 10 Hertz. Yet again, we get the value of voltage out in Cartesian form, and the magnitude of it in the command window. Cartesian and magnitude. And there's our diagram with the sawtooth wave being sent in, and the actual response from the RC circuit, which is pretty much what we expect. This is the steady state of the circuit. I'm gonna jump in quickly because I don't have that much time on the software to the sine wave, which is again basically the same piece of code with only one difference. I create a variable called sig with sine by 2 pi ft and a vector of t starting at 0 and ending at 7th second. So I'm just gonna evaluate that selection. Again, peak to peak voltage, frequency of say 1 Hertz, and forgot to mention, I also included the formula for the phase shift, or the shift angle between two sinusoids, which is given by this function here. Oops. Okay. Angle V out Cartesian Nice. Matlock not responding. There you go, and we should see a slight shift between two waves, which is clear. That peak does not correspond to the peak of the voltage sinusoid or the voltage signal being sent in, which is here. Grant. So we verified our sine wave. Yet again, I'm going to put emphasis on the fact that the magnitude decreases when frequency increases, and this is shown pretty explicitly with this piece of code, where I actually subplot 6 different sinusoids. Each plot will have a frequency incremented by 0.5 of a hertz. Here I start at the frequency of 0.5 and I go as far as 3 hertz. So we should see 6 plots with frequencies 0.5, 1, 1.5, 2, 2.5 and 3 hertz. And you will see that the magnitude or the amplitude of the signal being output is going to get relatively smaller each time I increment the frequency. So I'm just going to run that, and we're going to have to wait for the DAC light to actually collect the data. Oh, my bad. We need to, boom, terminate the operation. I need to close the figure, do it again, evaluate selection, and now let the DAC light collect the data. We should see the subplot of 6 different plots. We can see that the amplitude gets significantly smaller, with the frequency being only incremented by 5 hertz, or sorry, 0.5 of a hertz. And I will zoom in after we actually collect all 6 plots. One more. There you go. We can see, just zoom in, we can see that the amplitude of this sine wave is in fact much bigger than the frequency of this sine wave, which is not in the shape it's supposed to be, but that's due to the sampling frequency. That is my prediction anyway. We can see that the amplitude in one cycle, which is, I'll do my best to actually, there, okay, we should see, is much smaller here than it is in fact on the first plot. And we can even see how the magnitude number relates to each plot. This was just a quick demonstration of the 6 sinusoids being plotted at the same time, with the frequency being incremented by 0.5 hertz. I think we have all the signals, different waves, pretty much verified. Thanks for watching. I hope you enjoyed it.